the organizers and all of you coming early Monday morning. So my talk will be related in some aspects to Gary's talk. We'll also be talking about charge transport and in various conformal field theories and their holographic duals. The part of the work I'm going to focus on is done in collaboration with Andy Lucas, who's a graduate student at Harvard, and Paul Chesler, who's over here. So here's the outline of the topics I'm going to cover. I'm actually going to review some older work just to give you a perspective on some of the questions we're trying to understand. So like Gary, I'll begin by just talking about electrical transport in CFT3s. He already touched on some aspects of this. And then we'll add various perturbations to a CFT3. And I'm going to do this in a parallel manner, both in a toy CFT3 and also in holography. So we want to really, my ultimate objective is to really understand what's going on in holography from a field theory point of view. And we're not quite there yet, as you'll see. So I'm going to add a chemical potential, and again, this is a review of some of the things that Gary also mentioned. Then we're going to add a periodic chemical potential, and we'll find that holography does some things well, but other things not so well. And so the question, really the outstanding question, is what's missing in holography? And the short answer is monopoles, I think. So we'll come to that. All right, so let's talk about electrical transport in CFTs. So let's begin with an actual CFT. So here's a toy CFT in 2+1 dimensions. It's Dirac fermions with NF flavors coupled to some non-abelian gauge field, let's say. So there's also some global symmetries here, and there's going to be a global U1 that I'm always going to assume. So when I talk about electrical transport, I mean transport in that global U1 charge, which is completely distinct from certainly the SU-NC gauge field okay. So this kind of field theory you can analyze quite easily in a 1/NF expansion. And in that expansion, you can add, you can add a Maxwell term too, but you can show to all orders in 1/NF that it's a conformal field theory, and various exponents can all be computed in a systematic manner in the 1/NF expansion. The other approach to such a field theory is, of course, to do the 1/NC expansion. I don't think anyone knows how to do it for precisely this theory, but if you dress up this theory with a few other fields, you get things like the ABJM model. And so we believe that the large NC expansion is what holography is telling you. So we want to compare the results of those two approaches. So this holography, of course, gives you, is the mic working? Yeah. Gives you, in the simplest model for the ABJM model, a dual theory which is ADS4, and action which is the Einstein-Maxwell action, which Gary has also mentioned. So now if you take this particular theory, as I said, you can do the 1/NF expansion, and you can quite easily compute the conductivity. So if you look at precisely at NF equals infinity, you just have free Dirac fermions, which is the world's simplest CFT3. And at finite temperature, this is what you get for the conductivity from free Dirac fermions. At high frequencies, it reaches the value 1 that Gary mentioned. It has some units in ohms for Dirac fermions with electrical charges, and so we know that value precisely. And at low frequencies, you get this delta function with the strength of outer temperature. And where is that coming from? So here you have a system with particle symmetry, which is thermally excited. So you get a thermal gas of both particles and holes. And again, as Gary mentioned, the particles have their momentum and current parallel to each other, whereas the holes have the momentum current opposite to each other. So they're both carrying current in the same way, and the state has net zero momentum. But these thermally excited particles, keep going forever, as do these, and it's the thermally excited contribution that gives you this delta function. Okay, so that's the basic answer. It just takes a page of calculation to get that for free Dirac fermions. But that's at NF equals infinity. When you put in 1/NF corrections, you get something like this in the 1/NF expansion. So this gauge boson that's present, that can now have these particles collide with these holes. So they're going to collide with each other. They have equal and opposite momentum, and effectively there's nothing stopping them from just coming to rest after the collision. So that collision leads to a finite conductivity. You get some resistance and this is the kind of, that delta function gets broadened out, and you get a sigma of omega that looks like this. So since this is a 1 over NF expansion, the height of the peak is about NF, and the width is the order 1 over NF. So it's a very sharp peak, at least in the regime where you can control it. Yes?
That paper doesn't have a 1 over NF expansion.
All right, okay, fine. There's the next paper with myself, which hasn't, yeah, it doesn't have the F, but it has the F. Okay. Okay, so, but we are interested in small NF, and it is not at all clear whether this Drude-like picture will survive at small NF. So at small NF, you do holography, and this is the simplest Einstein-Maxwell theory, and as Gary has already told you, it has a rather trivial sigma of omega, which is just a constant, which is, as very, very different from this free weakly interacting limit. So you have to now add, precisely for that reason, we started thinking about, well, what else could you add? What are the corrections that are allowed? Now, Gary mentioned that you can add, sorry, there should be a Maxwell term here. You could add any power of f, and it won't change the answer. But it turns out, if you look at, don't think of it that way, but think in terms of number of derivatives. So this is the Einstein-Maxwell theory. And you look at terms with 4 derivatives then, in the holographic sense, and you find there's just one term allowed with 4 derivatives, which gives an effect to the linear conductivity. It's this Weil term. And once you put the Weil term here, you do get an interesting frequency dependence. So this is without the Weil term. You have a constant even at finite temperature. You put in the Weil term, and for gamma positive, you get a function that actually, well, is starting to look like the 1 over NF expansion, with a peak at 0 frequency and a dip here. But with the difference that it's not a very large peak. It's just a rather modest looking peak here with about a 33% correction to the conductivity. And I should also mention the value of gamma is bounded. There's a exact bound on gamma from stability criterion in the holographic theory, and also from the conformal side. And so if you take the largest possible value allowed, you get a rather modest frequency dependence. And in a very recent paper that I won't say much about, just came out on the archive last week, we compared some of these frequency dependencies with Monte Carlo results on a small n model like the Bose-Hubbard model, and find that it actually does rather well in fitting the frequency dependence. Okay, and there's also another curve that you get for negative gamma with a dip rather than a peak. And this we think of as something that might arise at your CFT, where it's better to think of it as CFT of nearly free vortices rather than nearly free particles. And finally, of course, the solvable models, as I've already mentioned, like the ABGM theory at n equals infinity, is just a constant answer. Okay, so that's really all I wanted to say about CFTs. We made quite a bit of progress and really beat this case a lot over the last 5 years, and there's now starting to be some convergence between the holographic picture and what we know from field theory. So it looks like things are in pretty good shape here. All right, so but we're not rarely interested purely in CFTs, so now let's add some perturbations. So we're going to add a constant chemical potential first. So here's my working CFT. I add a chemical potential term, and again, I'm sorry, this mu has nothing to do with that mu. But hopefully that's clear to all of you. So for chemical potential negative, you have you put your chemical potential here, so you only occupy states below this point, and the net result is you have what's called a Fermi surface. There's a line, a circle in momentum space, which separates the occupied from the empty states, and that's true for either mu less than 0 or mu greater than 0. So that's the condensed matter point of view, that you have this Fermi surface appearing, and this is going to change many of the physical properties. So that's at NF equals infinity. If you put in 1 over NF correction, which I'll briefly refer to shortly, of course the simple 1 electron picture doesn't remain, but the idea of the Fermi surface as controlling many of the properties is quite robust, as I'll argue, certainly in the 1 over NF expansion. And we're going to come back to that. But let's just start at NF equals infinity and now compute the conductivity. in the same spirit as what we've done before. And this kind of thing has been done a long time ago in the condensed matter literature in the context of graphene. And so you just compute the one loop diagram with this chemical potential. They did it even in the presence of disorder. So let me ignore that and just focus on their zero disorder curve. And this is what you find. You get at zero temperature and zero disorder, this sigma equals 1 in appropriate units at high frequencies. But then there seems to be a gap and a delta function right at zero frequency. So now this delta is purely a consequence now of a non-zero chemical potential. And the way you think about it, I guess, say in this picture, so if this is where your Fermi energy or your chemical potential is, let's go to high frequencies. At high frequencies, you're talking about taking electrons and giving them energy omega. Well, if your frequency is small, there's no place for them to go because these states are also occupied. So there's a threshold frequency above which you can now do the absorption. And up here, it doesn't matter whether there's a chemical potential or not. So that's why you get 1 up to this frequency and then nothing. But you get a delta function at zero frequency, which has to do with the fact that there are all these occupied states here, which can have a net for which there's no hole-like conjugate. So the current carrying state of the associated with this carries a net momentum, and you can't degrade the momentum because the momentum is conserved. And so that's why you get a delta function peak at zero frequency. And you can see also this very simple free electron model with this conductivity looking like this does a pretty reasonable job of, this is an actual experimental data, and this is 1 in physical units, that's the physical unit as measured in this experiment. And it's very accurately close to that. Okay, so holographically, as Gary's already reviewed, we have, when you apply a chemical potential, you have to put the boundary condition, appropriate boundary condition with the net electric field on the boundary, and the solution is the Reisner-Nordstrom solution, which at very low energies has an ADS 2 cross R2 near horizon metric. Okay, now you can do the calculation of the conductivity in this metric, and you get a result which again starts to resemble the field theory side. It's constant at high frequency. At zero temperature, it doesn't quite have the very sharp threshold that the free electron model had. It seems to have a more of a soft gap. But when you put in the 1 over NF correction from the photons, you'd also get a similar effect from the gauge field side. So the sharp gap was an artifact of the free electron model. And also you get a delta function at zero frequency. In fact, the coefficient of the delta function is just fixed by very general rules, and both holography and field theory obey that law for the coefficient of the delta function. So again, it seems like everything is working extremely well, and at least as far as the optical conductivity is concerned, and even the DC conductivity, there seems to be a good correspondence between holography and field theory. But there's one really striking difference, though. In the holographic model, first of all, we had no fermions. It was just pure Einstein-Maxwell theory. And it seems to be some kind of very featureless fluid that's carrying the charge in your electrical transport. Whereas on the field theory side, you had a very definite structure, and that was this Fermi surface. Everything is coming from this Fermi surface, and associated with the Fermi surface is a definite length scale, or a momentum, which is the Fermi momentum, the radius of the circle in momentum space. And that's really a crucial determinant of all the physical properties. So really one of the big questions, I think, in this correspondence is trying to understand, what about the Fermi surface, and are we really properly capturing the structure of the Fermi surface in holography? So more precisely, if you start with the CF33 in a chemical potential and do a 1 over NF expansion, then the fermions near the Fermi surface are coupled to this gauge field. And this leads to what we call in condensed matter a non-Fermi liquid. But that's not a terribly good name, because this non-Fermi liquid also really does know about the Fermi surface, but in a more subtle way. So if the fermions have this gauge charge, the single fermion Green's function is not a gauge invariant object. And that's the usual object you use in condensed matter. You look at the momentum distribution function of the electrons, and where that has a jump, you say, well, that's where the Fermi surface is. Well, if the momentum distribution function is not gauge invariance, you can't quite use that to detect the Fermi surface. And that's why we chose to call this Fermi surface as hidden, just to emphasize that it's not obviously there. However, it does have important effects. The Fermi wave vector does control correlation functions of other gauge invariant objects, such as the density operator. And if you looked at the spatial correlation of the density correlation function, you'd get what are called Friedel oscillations, which oscillate with the wave vector 2kF. On the other hand, if you took the Einstein-Maxwell theory, you'll see no sign of these Friedel oscillations. So that's a worry, but you might say, well, okay, let's not worry about it too much. It's some very weak oscillatory structure that's just not so important for charge transport properties. That may be a reasonable point of view, but anyway, it's something to keep in mind. Another quantity you could measure of this CFT3 in a chemical potential, which is quite hard to compute, but from various methods people are getting a handle on what it looks like, is the entanglement entropy. And our current understanding is to understand the entanglement entropy of this non-Fermi liquid, of the CFT3 in the 1/NF expansion. The dominant contribution, in fact, does indeed come from this Fermi surface, and that's the simplest way to understand what's going on. And so again, if you looked at the entanglement entropy from the holography side, you would run into problems in getting a correspondent of what the expected results are. Okay, so what am I doing on time? I have half an hour. So here's kind of a summary then of some basic properties of Fermi liquids. So if you just take free electrons, you know that they form a Fermi surface with a certain radius given by the density. The low energy excitations are particles and holes near the Fermi surface which disperse linearly with momentum. The entropy or the specific heat at low temperatures is linear, as you know from freshman solid state physics. And this is a very complicated way of writing down something that's linear in T. I just call it T to the D minus theta over Z. And then the entanglement entropy is known to have the violation of the area law. Here P is the boundary area or the perimeter in 2 dimensions, of the entangling region. And this violation of the area law it seems to believed to be rather unique to systems with Fermi surfaces. On the other hand, what we're interested in are Fermi surfaces coupled to a gauge field, and as I emphasized, that means this Fermi surface is not directly visible. And in fact, because of the damping from the gauge bosons, you get some diffuse set of excitation with scale with dynamic exponent z equals 3/2. But the other properties, the entropy density, when written in this clever way, and also the entanglement entropy behave in the same way as nearly free electrons, and it's in this sense that really this Fermi surface really is fundamental to determining the properties of the large NF expansion. So there's also another very interesting property of the entanglement entropy of a Fermi surface, which is that it has this P log P dependence on the perimeter of the entangling region, but also very curiously the coefficient of the P log P doesn't depend on the shape of the entangling region. If you change the shape while preserving the perimeter, this coefficient will not change. So this is a result that comes out of computations on the field theory side, and you would like to also reproduce it in holography. Okay, so then it turns out that if you focus not so much on these direct fermionic representations, but on the structure of the conformal field theory as measured by entropy and the entanglement entropy, then you can, in a sense, fine-tune the holography and get some dual metric which reproduces all of these properties. But the fine-tuning is bothersome, but it's not too bad because you have to tune one parameter, which is the value of theta. You pick theta to be d minus 1, and with this hyperscaling violating metric, you can reproduce all the basic properties of the entropy and the entanglement entropy. I should say this will work with Swingle and Hughes that I should have cited here. Yeah.
Yes. Could you comment? This first relation implies that Latinger theorem is
Correct.
valid.
In that, yeah, provided you measure kf appropriately.
Exactly.
Yes.
Exactly.
Yeah.
Okay. So when are you going to lose Latinger? To violate Latinger theorem, is it?
Well, there is, I believe if you have some compressible state in which the global U1 symmetry is not broken and the translational symmetry is also not broken. So you take any system at finite chemical potential, what it invariably will do, if you pick a random system, you add some finite density of particles and you cool it, it's either become a superfluid, in which case you break the global U1 symmetry, or become a solid, in which case you break the translational symmetry. But if you're able to find a system where neither of these two happen, then at low temperature, I believe there's always a Latinger theorem. It may require some subtle definition depending on the number of gauge charge and gauge neutral particles you have, but there will be a Latinger theorem relating some kind of sum rule on all the Fermi surfaces you have and the density that you've imposed. I don't think there's any way to get around it, which is really the why, and that's precisely the reason why I keep coming back to this point as something that holography should eventually also reproduce. All right, so I've reviewed then past work here on electrical transport in CFT3s and electrical transport and other properties in CFT3s in a constant chemical potential. And the basic take-home message is that for many things, holography is remarkably successful. But if you're really insisting on thinking about some of the properties of the Fermi surface, then it's clear that at least the simplest Einstein-Maxwell solution and its various deformations don't quite capture it. But they do capture some aspects of it. It's very tantalizing how close they get in many ways. All right, so now I'm going to talk about the announced topic, which is now take a periodic chemical potential. So unlike Gary, I'm going to not go all the way. He had both a constant background and a periodic potential. I'm just going to stick to the case with zero average. Okay, so here's the picture, one crude picture of what I want to do. So here's zero average, and if that was my voltage, I just have a CFT. And then I imagine putting in a positive voltage here and a negative voltage here in this sawtooth manner. And in fact, there are actually many experiments now on graphene where they do precisely this. They just lay down various gates under a film of graphene and measure the transport in two directions. And the results actually do correspond to some of the field theory results I'm going to show you. So if I take a Born-Oppenheimer point of view, which is an approximation, and just think of the system locally, then in this region I can think of a positive potential, so I deplete the number of, electrons are positively charged. I put a potential here that depletes the electrons, and therefore I get a Fermi surface of holes, locally anyway, if this went off to infinity. And conversely, on this side, I'll locally get a Fermi surface of electrons, and the picture is drawn carefully enough where the chemical potential then is the same height. What's being lifted up and down is the dispersion relation of the particles. So we have to now we are interested in transport along this direction, for example, and so we have to solve some sort of scattering problem and match things that are across this boundary. So it's a fairly simple problem, except you have to do it with Dirac fermions, and it has remarkably, even for this very simple free electron problem, some surprises. When you go beyond this simple picture of this local Fermi surfaces whose change in character from electron-like to hole-like every wavelength. Okay. Okay, so the first thing, let me just describe what happens for free electrons. So that's NF equals infinity in my conformal field theory. I want to do better than this very simple picture. So there's one dimensionless parameter that's going to determine everything now. You have a CFT, which is completely scale invariant, and you're perturbing it by a potential which is V of x, say this looks like this. And V of x has two dimension full parameters. One is V itself, the height of the potential, and the other is k, which is the inverse wavelength of the potential. They both have dimensions of energy, so there's only one dimensionless parameter around, which makes life simple, which is V over k. So I just have to vary V over k and figure out what does the spectrum of the system look like. So let's first take small v over k. So at small v over k, life is relatively simple. You have this Dirac fermion, which I'm now showing in momentum space, qx over qy are the two directions. Since my period is 2 pi over k, it means my new Brillouin zone along the x direction has width k. Everything is periodic then as a function of momentum k along this direction. So you get a whole bunch of states between qx equals minus a half and a half in units of k, which I'm not showing here, and everything repeats periodically in this direction. Nothing is periodic in this direction. So you had this Dirac cone right at the center, and you put in a small potential. So any particle here, when it hits the potential to first order in k, gets shifted by momentum k. So it gets shifted over here, and the original Dirac cone would be at higher energy. So effectively, it's mixing with the next band. So there's if you wish, an energy gap of order k. So the whole perturbation is completely regular. So as you do a perturbation in v over k, you won't see any problems. Everything is fine. You've just got the Dirac cone sitting there. Okay, so this is what we were doing, and we just said, okay, let's turn up v over k numerically and see what happens. And initially, we found that we were surprised at what happened, and then we looked up the literature and found this was actually well known by many people in the graphene community. And this is what happened. So this is now much larger v over k. Again, things are periodic in this direction, but in the y direction, you start developing another minimum, and you can't quite see it here, but there's another Dirac point over there. And you turn up more and more and more, you get more and more Dirac points appearing along this direction. So the low energy theory, which initially had one Dirac fermion, at a certain point has 3 of them, and then it has 5 of them, and so on and so forth, up to very large values of v over k. This is just for free fermions. And here's another picture of the dispersion and the color plot. This is the periodic direction, and that's the aperiodic direction. At small v over k, you have one Dirac node here, and you can see one here and another there. And then at alpha v over k, there's one here, another there, and another one over there, and that's it. So there's a finite number at any value of v over k, but that number is not just 1, it's any odd integer. And if you now look at the positions of this, at least for the square well, there's a simple way to understand where these Dirac nodes coming from. They're coming from the fact that you had a Fermi surface. Okay, so the Fermi, you try to get rid of the Fermi surface, but you can't. So here in dashed line is the original Fermi surface before you had a periodic potential. So you turn on some V. Imagine you turn on a V which is uniform. Then you get a Fermi surface that looks like this. So that Fermi surface, it's the same as these two Fermi surfaces. There's a Fermi surface here and a Fermi surface there. They have the same radii because I've taken a square well, and that's that Fermi surface over there. I draw over here. Okay, so then what are these lines? Well, everything is periodic in k. So there's reflection. Momenta is only defined mod k. So everything has to be folded back into the fundamental Brillouin zone or the fundamental region, which has width minus k over 2. So I take this big Fermi surface and just fold it back over and over again. If you fold it back, you get this line and the other one. Okay, so the zigzag line is just the original Fermi surface folded back because things are only defined mod k. So you have these two electron and hole Fermi surfaces going around, and remarkably, you find the points that they intersect. These points are the Dirac points. So they're exactly the location of the Dirac points. So you had a Fermi surface, you put it in a periodic potential, and when you fold things back, you get these Dirac points. And now you can see as you make V bigger and bigger and bigger, you get more and more intersections as you fold it back. And they emerge from here and keep moving up. So that's what those Dirac points are. They have to do with the existence of locally a Fermi surface when you apply a chemical potential. So now so you can see again that this whole picture, I was talking about free fermions, but in all orders in the 1 over NF expansion, this is going to survive. And in fact, it's going to make life even simpler in a sense, because once you put in the gauge field corrections, you expect the velocities at all these points to also renormalize to a common value. So in the end, what we haven't proven this, but what a very likely result of the 1 over NF expansion, that the infrared in the IR you get another CFT. You started with a CFT, you perturbed it with a periodic potential, and you end up at very low energies with another CFT, which is not the same as the one you started with. It's a CFT which has not NF Dirac fermions, but ND times NF, where ND is the number of Dirac points, which is actually an odd integer and jumps in not unit steps, but double steps at some values of peak V over K. So you get these discrete jumps between different CFTs as you increase the value of V over K.
The overall theory is still scale invariant?
Yes, yes. It's scale invariant asymptotically low energy regime, but with different CFTs. And in fact, right at the transition points, it's not a CFT. It's scale invariant, but it's not a CFT. So in between the transition points is again a CFT. So it's a rather complicated flow, but that's the picture. To all orders, well, in the 1 over NF expansion. All right, so then what about electrical transport? So you go ahead and compute the electrical conductivity as a function of frequency now at 0 temperature, both for small and large V over K. So again here the answer before we put in any perturbation was 1, or now, okay, this is for Dirac fermions, the answer is 1/16 in appropriate units there, and so that's why these numbers are small. You put in a perturbation and you get kind of a dip around V over K equals 1, and okay, you'll see this at small V over K nothing much happened. This is somehow the periodic potential leading to some sort of resonance in sigma of omega. And at large V over K, you get actually a very sharp peak again at omega of order K, and various resonances. These are interband transitions at larger frequency, and again asymptotic to the 1/16 value at finite large frequency. But so this seems naively what you might have expected, and in fact this is what we computed first, and we said, oh well, everything is well understood. But if you look at the 0 frequency value, it seems to, well, it's not obvious from the way I plotted it, it's much larger in this case than the high frequency value, whereas here it was almost the same as the high frequency value. So let's just take the 0 frequency value, the DC conductivity, and plot it as a function of V over K. And when you do that, this is what you get. You get a very oscillatory function of the DC conductivity, which is measuring the very low frequency transport. And in fact, what these peaks are precisely these points where the IR CFT changes. So they're the points where these Dirac points are emerging in pairs at very low energies, and these new Dirac points, every time they emerge, right at the transition point gives you a peak in the DC conductivity. In between the Dirac of the transition, there seems to be rather smooth development as a function of V over K, but these are then features of the NF equals infinity theory, which we again expect will survive when NF is large enough, although we haven't done that computation. It's quite messy, but there's no reason to expect the peaks to completely disappear at large enough NF.
Sorry, question.
Yes.
These are results from free field theory.
Yes.
Okay.
It's free electrons, really, that's all. It's still quite a messy calculation, and this is what you get. There are analogs of some of this that's been seen in the experiments, which are cited in our paper. Yeah.
Do they appear at 0 at K equals 0, the Dirac nodes?
Yes.
Okay.
So they appear. So the pair creation of the Dirac nodes happens at this
Happens
point.
at K equals 0. Okay.
If you just take this picture and just keep drawing it as you increase the radius, you'll see how this picture explains exactly how they appear. It's just a matter of folding back the Fermi surface in the original Brillouin zone. Okay, so what does holography do? So following the nice work of George and Gary, this is a simpler case of what they looked at. And so we did a similar numerical solution of the Einstein-Maxwell's equation in the presence of a periodic potential. But here we can also use another technique because we believe you're asymptotically ADS4. You can do perturbation theory in V over K using Witten diagrams, and this is also done. And I won't go into detail, but essentially consistent results were obtained. And for all values of V over K, the deep IR is just a CFT. And we don't see any evidence of any phase transitions, and everything's made change smoothly as a function of V over K. Then you can go ahead and compute the conductivity and compare with the field theory. So this was the large NF result, the free fermion result with this dip at omega over K. And not bad at all. That's roughly what you get from holography also, with a dip at order omega over K. This is coming from solving, just summing 3 Witten diagrams for the conductivity, and also numerically you get very similar results. And at large V over K, we had the sharp peak at omega over K of order 1. You don't get such a sharp peak, but again you get a feature which has the general structure of a peak at omega of order K. And here there's also like a dip and then a reconstruction, as it has to be because you want to satisfy some sum rule, and that's sort of what you get, and it reaches up. So this all looks, really remarkably similar given the differences of the model. This is free fermion, this is Einstein-Maxwell's equation. And it'd be insane to imagine they were talking about the same system, but they are, which is really the amazing thing, of course. But if you look at the DC conductivity as a function of V over K, there is no sign at all of these resonances. These discrete phase transitions where the Dirac fermions were created are just completely absent from the holographic theory. And as I emphasized, these phase transitions have very much to do with the Fermi surfaces that are present in the CFT at finite chemical potential. But if you look at the background or the average, well, they look roughly the same. So and certainly you expect these peaks to become less sharp as you make NF smaller because of damping from the gauge bosons. But there's certainly some oscillatory structure here that's not completely missing from holography. So how much time do I have then? 5 minutes or so?
Yeah, 2 minutes.
Okay, so
Last question.
all right. So let me then, so how do I resolve this? But we haven't fully resolved it by any means, but let me give you some evidence that the answer comes from monopoles. So we are missing certain aspects of CFT3 so far that you have to put back in the holographic story. So this is sort of the question that I started with, which seemed like a kind of esoteric question when we were talking about Friedel oscillations, some very weak oscillations, density correlations, but now seems to have become a much more pressing question once you have the periodic potential even in the presence, even in the DC conductivity. So the proposal that the answer has to do with monopoles was made by Faulkner and Iqbal in the simpler case of one dimension, where they in fact showed in a very nice calculation that once you put in bulk monopoles in the 2+1 dimensional bulk theory, that you could reproduce Friedel oscillations in the density correlation function of the boundary CFT. Okay, so what we've done is an analog of that in 2+1 dimensions. Let me just skip that. So 2+1 dimension, the monopoles are a somewhat more subtle concept because we're not talking about monopoles here in the gauge theory. We're talking about monopoles in a global U1. So we're talking about a general CFT in 2+1 dimension, which has a global U1. And generally, such a theory doesn't have dynamical monopoles. Those are monopoles, Polyakov monopoles are monopoles in a dynamical gauge field. But you can talk about what you call a monopole insertion. So even for the simplest XY model, or the Wilson-Fisher fixed point of a complex scalar field, you can put in an insertion of a magnetic field, which is a static insertion whose flux looks like that of a monopole. And the CFT responds to this insertion in a rather well-defined way and gives you the analog of a scaling dimension, which you can compute in 1 over NF expansion, and we have done some of that, and Pufu especially done that in a variety of papers in many different CFTs. So there are these monopole operators that can be inserted and are essential to the structure of a CFT. Now, it turns out that to define these monopoles in the holographic theory is actually quite simple. So what we do is we introduce some scalar field phi m, which is dual to the monopole operator to the CFT, monopole insertion, I should say, and that scalar field couples to a gauge field, which is the S dual of the four-dimensional holographic dual. So now we can just take the usual electromagnetic dual in 4 dimensions, dA twiddle, and you put in a field that's charged under this gauge field. So there's no average value of this field because there's no average, sorry. So the system that you started with has an electric field because you had finite chemical potential. So when you take the S dual, there's an average magnetic field. So A tilde is like a magnetic field then acting on this monopole scalar that you put in the bulk theory. So why do I think this has anything to do with these Friedel oscillations and Fermi surfaces? Well, if you add such an operator to your holographic theory, it's not easy to figure out what comes out in general, but there's one limit where you can work things out, and that's where you just condense it. So if you just condense the phi m, you find that you get a vortex lattice because you have a scalar condensing in a magnetic field. But the important thing about the vortex lattice is that it has exactly the right period that you would expect if you formed a crystal. So if your CFT, as I said earlier, if you take a CFT and apply a chemical potential, one of the things that could do very easily is form a solid, or what's called a Wigner crystal. And that solid has a very specific period. It has a period so that per unit cell of the solid, there are integer number of particles. That's what a regular spontaneous solid looks like. Solid helium has an integer number of helium atoms per unit cell. And that's exactly what happens here. You get the right, the monopole operator has quantized your charge, and you get an integer number of electrical charges per unit cell. And that means you've got a solid in the direct frame of reference. And it's the same period, and since you've got the right crystalline period, you might think it also knows something about Fermi surfaces in a regime where the vortex lattice is fluctuating. In a recent work, we have looked at the back reaction of the vortex lattice on the metric, and it seems like this reaction diverges in the IR, so we don't know ultimately what happens in the IR. It's very different from the electrical lattices that Gary is talking about, which decay in the IR. This seems to blow up in the IR when you put a magnetic flux, and that suggests that you're making some phase transition to a solid, which is just some confining state. So the open questions are: does the vortex liquid-like state of this monopole operator eventually give you the Friedel oscillations, and will it lead to also the missing oscillatory behavior and the conductivity in a periodic potential from the holographic point of view? I think these are questions that are quite important and rather difficult and have not been answered. So I'll stop right there.
If in your oscillating potential you add the constant term, I would presume that you should see a transition between an ADS4 and an ADS2 at some point as a function.
In the holographic point of view?
Yes.
Yes, that's correct. Yeah. Yes.
Is that a phase transition?
I don't think so. I think there's some crossover. That's probably in Gary's results, right? I mean, I don't know if you have studied it in intermediate ADS4, but in some appropriate regime, it must be there in your numerics. Yeah. And from the field theory point of view, this picture, basically holds even at finite chemical potential. You have Dirac cones coming out of each of these black points, and all you do is you just take a Fermi surface around that. So you will get many Fermi surfaces, multiple Fermi surfaces whose number keeps changing as you change the periodic potential. So there will be very strange effects even at finite chemical potential here, which are associated with these Fermi surfaces and these emergent Dirac points.
But is this stable against the gauge interaction now in the far infrared?
It is. It's stable. Because really, all you do is just take a low energy Dirac point, and once you do that, provided they're well separated, it doesn't matter that really at finite momentum, it looks the same. Yeah.
At large V over K,
Yeah.
you must have alternating ADS2. That's the Born-Oppenheimer limit. Is that right?
In the holographic point of view.
Yeah. So
Yes.
there must be alternating ADS2.
Yeah. So we studied some of that, especially Andy. In fact, that's how we started out. We said how to match these ADS2 together. Maybe they'll give you some new emergent frequency scale. And
This peak surely is that.
yeah, it's related to that, but yeah. But we were wondering whether there were some strange powers in the width of this peak. But I think the final answer didn't seem to be everything was just omega over k.
This looks like it's a ADS2 Judah peak that's just been shifted.
It's something like that, yes. And so that shifting comes from the tunneling between the different regions,
Right.
as it does also in the field theory side.
Okay, let's thanks Bill.